multiplication of functions.
Right. So I mean, there is some generating function out there. Everything is a generating function, but I see no reason to believe that they're rational.
Are you going to offer any $1,000 bets?
Oh, absolutely not. I have not thought about it enough to actually put money on it. All right. So some new definitions. All right, so we already talked about left-right mins. So for each left-right min, we have an activated sequence. And the activated sequence is all the letters above and after it. So everything that comes after it, that's bigger. And the way to think about these activated sequences are these are all of the letters that could end up forming a forbidden pattern with that left-right min. So if that left-right min is going to be involved in some sort of forbidden pattern, it's going to be with these elements of its activated sequence. The other new definition, or one of the other ones, requires us to make an observation first, which is that for each non, so if I don't have a left-right min, if I come up with some new letter that is not bigger, or is not smaller than everything that came before it, all the letters larger than it, the letters larger than it, have to all be letters larger than it that follow it. So everything that comes after it that's bigger, they all have to be decreasing. And they all have to be decreasing because otherwise we're going to have a 1, 2, 3, 4 pattern. And because they're all decreasing, and so we know exactly what order they come in, we'll call them fixed. So let's call them fixed. And finally, if everything greater than some left-right min, is fixed, that left-right min is deactivated along with its activated sequence. So what this is saying is that, let's say that we know exactly the order that everything comes in above some left-right min. That means that we know for sure either there's a problem, either that left-right min is going to contribute to a forbidden sequence, or for sure there's no problem, there's no possible way for that left-right min to contribute to a forbidden sequence. But we know for sure. And we're thinking about activated sequences as being sequences that we have to keep track of because we don't know for sure whether they're going to cause a problem yet. But once we do know for sure, we can just forget about them. Either there's a problem or there isn't. So that's why we would say at that point that they're deactivated. All right, so now let's start writing down the actual object that we're going to enumerate. So what's the analog to A of our little a, b, and l? So first of all, R is going to be the same as it was earlier. And, I guess I should have written K in here too, because this certainly also does depend on K. I will be writing K over here now. So I'm going to, A is actually, it's going to play the same role as it did over there, but I want to define it more precisely than I did earlier. So A is going to be some number. It's going to be some number such that no copies of 1 up to A have been used yet. Have been used so far. It's not necessarily the largest such number, it's just a number such that no copies have been used so far. Eventually we will have a canonical choice for A, but we don't have the ability at this point in the talk to say what that choice is. The other things that we're going to need to define are M, and M is a list of left to right minimums. And we're going to say that the length of M is U, so this is just notation. And then S, this is my attempt at a script S, is a list of activated sequences. And so each element of S, so there's also U elements of S, and each element of S is the activated sequence of the corresponding element of M. And then the last thing that I need, so the last piece of this is going to be L, which is going to be basically the same thing that it was in the last argument, or the last case that we did. The last piece is L, and L is just, what do I want to call L? L is just a list of letter counts. A list of letter counts for all letters greater than or equal to A. Or sorry, strictly greater than A. So everything up to A we know has R copies left, but everything above A, we don't know how many copies are left, so we store that information in L so that we do know. Alright, so now we actually state this quantity that we want to enumerate. A of R, K, A, M, S, and L is the number of words. I'm just going to say, yeah, okay, sure, so I'll say also the full thing. So the number of words using R copies of 1 through A, and L sub I of A plus I, the void 1, 2, 3, 4, and 1k, k minus 1 through 2, even when prepended, or even when preceded, I should say, preceded by M1, so this left right min, followed by its activated sequence, M2 followed by its activated sequence, or M3 followed by its, MU followed by its activated sequence. So the way that we want to think about these, though, is similar to the way that we wanted to think about A earlier. We're building this word letter by letter by letter, and at some point in time, we have this list of left to right minima, we have this list of activated sequences, and we have remaining letter counts left to be used given by L and A. How many ways are there to finish this word? That's what A is really measuring.
So for each of these is really a state.
Each of these is right. So this is a state governed by the parameters. Well, essentially, if we treat R and K as fixed, it's governed by the parameters M, S, and L.
That's why you have so many of them.
And that's why we have so many of them, because there's exponentially many choices for M, S, and L. Or exponentially in my parameters R and K. Fortunately, it doesn't depend on A, which is why these end up being finite recurrences. All right, so 9 minutes left. So let me give you an example. So I might just end up stating some of the last theorems, but that's fine. That was my plan anyway. I didn't even write down a proof to bring here.
Good job at preparation.
Well, I figured if I wrote it down, I might be tempted to go through the proof, and no one wants that. All right, so for example, let's say that we're building a word on, so the alphabet with the letters 1 up through 9, where each one is repeated twice, or each one, there's 2 copies of each one. And so far, we have 6, 9, 9, 4, 5. So here's what we've got so far. How many ways are there to finish this word? Well, let's notice the left to right minima are 6 and 4. But then notice that 5 is not a left to right minimum, which means that all of the elements less than 5, or bigger than 5, are fixed, which means that everything bigger than this left to right minimum, including 7 and 8, are all fixed. And so this guy's actually been deactivated. And once it's deactivated, we don't count it in here anymore. It's no longer a left to right minimum that we care about. So actually, the way we would count this quantity is it would be A, so 2, because R is 2. Oh, and I should tell you what we're avoiding. So we're avoiding 1, 2, 3, 4, and 1, 5, 4, 3, 2, 1. So R is 2, K is 5, and then 3 is just some number such that I haven't used any copies of 1 up through 3 yet. Okay, so now
1, 5, 4, 3, 2.
1, 5, 4, 3, 2, right? So let me also say that in order to make these things finite, I have to have some way of making sure that they don't go all the way up. So like, A can be very, very large. A can be arbitrarily large. But I don't want the elements of M, S, and L to M and S to also be arbitrarily large, or else I lose my finite recurrences. So I essentially normalize these by just subtracting A from each element of M and subtracting A from each element of S. So instead of having a 4 here, because my left-right minimum is a 4, I have a 1 here, because 4 minus 3 is 1. And then my S is going to be 5, but I subtract off 3 to make it 2. And then L is going to be 1, 1, 2, 2, 2. All right, so again, this is just sort of a bookkeeping thing to make sure that my recurrences actually are finite. I'm certainly allowed to do this. I certainly won't ever end up with negative numbers because I know that I haven't touched, and I know that I can't have a left-right minimum that's below 3 or some element of an activated sequence that's below 3 because I haven't touched the numbers below 3 at all yet. Okay, so while I erase this, notice that that's not the unique way to write the number of ways of completing this word. So if I made a different choice for A, then I would get different arguments to this function. And that's not really a problem in principle, like everything's still well defined, but it is kind of annoying. And so again, eventually we'll make sure that there's only one canonical way to write this. All right, so wrong notebook. Theorem. A is well defined. So it's not immediately obvious that this is true because there's lots of ways to make to give A all of these arguments. For instance, if I just got rid of all of the elements up until 4 and 5, I would get the same arguments because I ignored 6, 9, and 9 as I was writing out M and S. So it's not immediately obvious that A is well defined, but it is true. And the reason, just very, very, very sketchily, is that M and S let you recreate exact subword formed by the LTR mins and the activated sequences. And then no other, so nothing that's not a left to right min or an activated sequence can participate in a forbidden pattern. I just gonna say be bad. So nothing that's not either a left to right min or part of an activated sequence can cause a problem for us. Or if it did, we would already know about it. We would already know that we were guaranteed to have a problem, and we would have stopped looking along this branch a long time ago. All right, so the next theorem is that all arguments to A take on finitely many values, where this finite number depends on R and K. So it depends on R and K. And the actual bounds that we get are that T is less than or equal to 6, K minus 2 plus 1, U is less than or equal to 2R times K minus 2 plus 1, and the size of any S is less than or equal to 2R K minus 2. So these can be large numbers if K and R are large, but they're at least always finite. So I am not going to state the recurrence because it's complicated. So all I will say to conclude is I want to conclude by saying that while I want to conclude on sort of a downer, which is that while we are guaranteed rational generating functions from all of this, because there's so many states, it is very hard. It takes a long time to actually get them. And so again, it's much better than just brute force, but it still needs some improvement before we can actually see these generating functions for non-trivial R and K. But at least now we know that they exist and they're rational. So that's kind of cool. And maybe I'll just write down the number of states that these recurrences have, just for fun. So this is the upper bound. It might be less. If I'm pretty sure that I can be clever and make it at least somewhat less. But here's what it is right now. So this is to the power of 2RK minus 2 plus 1 times 6K minus 2 plus 1 to the power of 2R K minus 2 plus 1 times 2R K minus 2. So it's for non-trivial R and K, there's a lot of states. But hopefully with more work, we can bring this number down a little bit. All right. So I think that's all I've got for you.
Thank you very much. Thank you, Yonah. You're not here to answer questions in private. Thank you.